Welcome to my presentation on the dynamic extension of the intrinsic time field in the T0 model. My name is Johan. In this presentation, I introduce a significant conceptual advancement, the extension of the static time field T of x to a fully dynamic field T of x and t that depends on both space and time. This extension brings us closer to a complete field-theoretic treatment. The T0 model has already established crucial concepts in its previous formulations. These include the intrinsic time field T of x, defined as Planck constant h bar divided by the maximum of mass times c squared and frequency omega. It has inverted the traditional relationship between time and mass and provides a framework for unifying quantum mechanics and relativity theory. In the current extension, we evolve from the static field T of x to the dynamic field T of x and t, treating both mass and frequency as space-time dependent variables and aligning the model with field-theoretic principles. The dynamic intrinsic time field extends the definition to T of x and t equals h bar divided by the maximum of m of x and t times c squared, and omega of x and t. For massive particles, this reduces to T of x and t equals h bar divided by m of x and t times c squared, and for wave systems to T of x and t equals h bar divided by omega of x and t. This extension has profound physical significance. The field responds to gravitational environments, mediates energy conservation in photon propagation, controls quantum decoherence rates, and propagates changes at finite speed, ensuring causality. The Lagrangian density for the dynamic time field comprises three essential components: a kinetic term with partial derivatives, a self-interaction term proportional to the square of the field, and a coupling term representing the interaction between the field and the matter-energy distribution. From this Lagrangian density, the Euler-Lagrange equation yields the field equation that describes how the intrinsic time field evolves in response to changes in the matter-energy distribution. This field equation is crucial for understanding gravitational waves and dynamic cosmological evolution within the T0 model. The dynamic extension of the time field necessitates a corresponding extension of the Schrödinger equation. In addition to the term T of x and t multiplied by partial psi over partial t, the total time derivative of the field now appears, accounting for both explicit time dependence and changes along the trajectory of the quantum system. This extended equation provides key insights. Quantum evolution is path-dependent, there is direct coupling between velocity and quantum state, gravitation directly influences quantum behavior, and time dilation effects arise naturally through mass variation. A particularly elegant feature of the dynamic time field is its handling of wave-particle duality through the Max function in its definition. During measurement, the m of x and t times c squared term dominates, leading to particle-like behavior. During free evolution, omega of x and t dominates, resulting in wave-like behavior. Compared to the extended standard model, which uses a logarithmic relationship, the T0 model offers a more direct and intuitive physical interpretation of transitions between wave and particle behavior. The dynamic extension of the T0 model has far-reaching implications in various domains. In the gravitational realm, it explains phase shifts in quantum interference, redshift as energy attenuation, and provides a unified treatment of quantum systems in gravitational fields. For measurement processes, it offers a natural explanation for wave function collapse, the transition from quantum to classical regimes, and links decoherence rates to local time field values. In cosmology, it enables a modified approach to early universe physics, accounts for time-varying gravitational environments, and integrates into an emergent gravitation framework. The dynamic extension of the intrinsic time field represents a significant conceptual advancement. It enables deeper field-theoretic treatment aligned with QFT principles, improves the description of quantum systems in varying gravitational fields, provides a more natural framework for wave-particle transitions, and encompasses comprehensive quantum evolution accounting for the total time derivative. The core principles of the T0 model are maintained: absolute time, variable mass, and emergent gravitation. This extension enhances the model's explanatory power, improves its theoretical consistency, and offers a unified approach to quantum and gravitational phenomena. This dynamic extension opens several promising research directions. Experimentally and numerically, we plan simulations of quantum evolution in varying gravitational fields, experiments to distinguish between T0 predictions and conventional quantum mechanics, and applications to cosmological models of the early universe. Theoretically, we will investigate wave-particle transitions during measurement processes, explore decoherence mechanisms in the dynamic time field, and pursue full quantization of the time field, potentially opening new approaches to quantum gravity. Specific research focuses include neutron interferometry in gravitational gradients, CMB spectrum predictions with T0 corrections, and galaxy rotation curves without dark matter. In summary, we have extended the static field T of X to a fully dynamic field T of X and T, developed a complete Lagrangian formulation, derived an extended Schrödinger equation with total time derivative, and enhanced understanding of wave-particle duality via the Max function. This extension represents a significant conceptual advancement, not merely a mathematical refinement. It provides a unified framework for quantum and gravitational phenomena while maintaining core principles and extending theoretical scope. Resources for further study include complete mathematical derivations, comparisons with the extended standard model, and implementation guides for numerical simulations. Thank you for your attention.